right, so I want to start with kind of a little thought problem. So this is a planet or a charged particle, something like that, and we're moving another mass or another charge around this thing. So let's say they start. So maybe it's easier to think of them as mass, but either way, we start right on the surface here, right at this one, and we move this direction. So we're moving directly away from the center of this thing. Does the field, does the gravity or the electric field, does that do work on that path? Yeah. Yeah, force times distance, right? Now, let's say we move directly angularly. We stay the same distance. Does the force do any work on that particle moving that path, on that path? No. Yeah, it's a level curve, right? The force, since the force is only proportional to the distance away, it doesn't do any work. And then if we go this way again, does it do some work there? Yeah. How about if we go this way at the same distance here? No. Here, does some work. If I go around here, no work, right? If I go here, it does some work. So really, all that matters is if I'm going to make a dotted line here. All that matters is where we started and how far away we ended up, right? Because all these curves here where we stayed the same distance, the force didn't do any work. So all that mattered was where we started, where we ended up. And I could go on any path. I could do some kind of whatever I wanted. And all that would matter is how far away from this thing I ended up. All this other stuff in between doesn't matter. Well, it turns out that for any conservative field, if we do a line integral, if we think of the work, the line integral over a path only depends on the initial and the final point. So the line integral along this path would only depend on the initial point and the final point, initial point and the final point. All right, so I'm going to, this is the idea that we're talking about today. All right, so remember that F is conservative. And I think we saw this maybe on our quiz. F is conservative if and only if F equals del cross F, where F, the small f, is the scalar potential function. So this leads us to our major result today. No. Because small f is a scalar function. The fundamental theorem of line integrals. So there are not a lot of fundamental theorems that we learn in math. We know the fundamental theorem of arithmetic, fundamental theorem of algebra, fundamental theorem of calculus. Now we have the fundamental theorem of line integrals. Fundamental theorem of line integrals, I'm going to write it for a vector field in the plane we could extend it to 3 dimensions or more dimensions just by adding a component. All right, so we're going to say for a path, C is given by some vector valued function, and that's going to be x of t I hat plus y of t j hat in the plane for a less than or equal to t less than or equal to b, and this is in some open region R in the plane. So we have this path in the plane, and we're going to say if our vector field, and we're going to write it as m I hat plus n j hat. If this field is conservative, in the region, and n and m are continuous, so n and m are nice functions. I'm not going to write that down. Then the line integral over C of f dot dr is equal to, because f is conservative, del f for our scalar field dot dr, and this equals the scalar field evaluated at B. This is a small f. This is, yeah, this is the small f. Comma y of B minus the scalar field evaluated at A. So this is very similar to the fundamental theorem of calculus, where we evaluate an integral on an interval. We evaluate that integral, that definite integral, by evaluating some related function at the endpoints. The related function that we use in calculus 1 was the antiderivative. Here our related function is the potential function. And we're saying f is conservative, so f, our force, our field, f of xy is del f of xy, and C is piecewise smooth. So we can evaluate that line integral if f is conservative, if our field is conservative. We don't care what the path is. We just evaluate the potential function at the endpoints. It's a very nice thing. All right. Well, let's look at why. We can see why this is. Are we good? Are we good with our fundamental theorem? All right. Well, no, you don't have to evaluate the integral. You just have to find the potential function. Yeah. So the potential function is kind of like finding the antiderivative. Yeah.
Sorry, I just didn't know.
Yeah. Nope. That's what makes it nice. But there are other nice things. But let's talk about why first. All right. We said f is conservative. So f is the gradient of some potential function. And I'm going to write this in differential form. That's going to be df partial of f with respect to x I hat plus a partial of little f with respect to y j hat. That's what del f is. So the line integral over our path of f dot dr equals the line integral of, we know to evaluate these line integrals, f dot r prime dt. And in this case, it's going to equal the integral from a to b, the dot product of f dot r prime. This is f, and r prime is dx dt I hat plus dy dt j hat. So that's going to be the integral of the partial of f with respect to x. Let me rewrite that f in my computer. Dx dt plus the partial of f with respect to y, dy dt, dt. This quantity, what is this thing? Partial of f with respect to x times dx dt is not similar to the total differential. This is by the chain rule for multivariable functions. Isn't this the derivative with respect to t of f of xy?
Right. Yep.
By the chain rule, this is the integral from a to b of the derivative with respect to t of f of x of t, y of t, dt. Well, what is the integral of a derivative? The function, and we have a definite integral. So isn't that just the function evaluated at the endpoints? So this equals f of x of b, y of b, minus f of x of a, y of a, by the fundamental theorem of calculus. So because our field is conservative, it's the gradient of a potential function, our line integral becomes the integral of a derivative. All right. So this gives us a very powerful tool for evaluating line integrals. So let's think for a second. What happens if we have a conservative field and our path, r of t, is closed? A equals b.
Zero.
What is the line integral around a closed path for a conservative field equal? Zero. Nothing changes. Right. So if a equals b, our beginning point equals our end point, the line integral around our curve of f dot dr equals 0 if f is conservative. Around any closed path. So if f is conservative, the line integral around a closed path is 0. Well, we have a nice notation for this. The line integral around a closed path we do this. And we usually we indicate the orientation of our path. So we draw a little arrow on here. So this would mean we go around the closed curve counterclockwise.
Wait, can we really write arrow?
Yes, because if we go the other direction, if it's not a closed path, the line integral changes sign.
But if it's closed.
If it's closed, then the line integral, if it's closed and f is conservative.
So that's for any closed path, not just conservative.
This is for any closed path. And eventually we'll have double integrals.
What does that mean?
The circle means it's a closed path, and the arrow is the orientation around the closed path. So we're going counterclockwise in this case. So I could say, or we could go this f dot dr for opposite orientation.
I'm gonna put that on F.
There's probably
We will talk about the double integral. We'll have surface integrals. So we'll have a double integral over a surface, a closed surface. We put a circle through the double integrals. And we can have a triple integral. We have a closed solid. You do a circle through your three integrals.
What does it mean a closed surface? Does that mean it has an edge? Or is it all surfaces?
No, because a paraboloid is open.
Oh, it's open on the top. So
Open on the top.
This means it's almost like you've created a solid object.
Right.
But you're just talking about
You-
the surface area of a solid object.
mhm.
Okay.
All right, we can make the same argument for 3 variables, 4 variables, whatever we want. We just add a component to our field, add a component to our vector valued function that describes our path, and we're set. So what this implies, if f is conservative and continuous in some region, so our field is nice functions, the line integral of f, our field, along any curve from one fixed point to the other has the same value. The integral is independent, the line integral is independent of the path. So we're going to state that as a theorem. So we good so far? This doesn't have a special name, so we're just got to call it a theorem.
Beamer theorem.
Oh, we have another one.
Pretty sure there is a
Theorem.
I feel like there is. Just theorem.
In our book, it probably gives it a number, 15 point something. So our theorem, if our vector field is continuous, on an open region, I need one other thing. Open connected region. Then the line integral of c of f dot dr is independent of path if and only if f is conservative. So connected means just what you think. So this region is connected. So I guess to make it open, I'd make the boundary dotted. This, if this were our region, that region is not connected.
So like, for example, like a hyperbola. Oh. If you were drawing a hyperbola on the xy plane, that would not be connected.
Right.
Oh.
Like the area.
Let me draw a little face. I know.
So if we had a path that went from here to here, that would not be in an open connected region. So that's our curve. That's our curve. This is not connected.
It's like the area itself of the region.
Right. Yeah, it has to be able to be enclosed by one boundary.
However, if you had a curve in that second figure that was completely contained by one
Right,
of
by
the
one of
cells,
those.
it would be fine.
In that region.
And then that would be
In that I guess that sub-region, yes.
Okay.
But if we try to make a path between the two, then you can't use this conclusion. All right. Questions so far? And remember, one more reminder. F is conservative. If what is true?
Partials are equal. If it.
If currently f the gradient is equal to a gradient
Del cross F
equals 0.
equals 0.
And then there's a few shorthand ways to test for that.
Hey, I did that.
In the plane,
You can do the partials.
Equate partials.
dm dy equals dn dx. So our test for conservative fields, the curl is 0, or if these mixed partials are equal. All right, so this gives us options now when we're evaluating line integrals. So for conservative vector fields, if f is conservative, we have 3 options. For evaluating line integrals. Our first one, we can always just evaluate it as is. We know how to evaluate line integrals. We just parameterize our curve and represent f in terms of the parameterized curve and evaluate the integral f dot dr. Sometimes this is
Very hard.
difficult and or tedious. For example, if you had a piecewise smooth curve with a bunch of different parts, where you have to parameterize each different part. You could end up with difficult integrals as well. The second possibility is integrate the components of f to find the potential function. And we know how to do this. We've done this type of thing before. Find the potential function and use the fundamental theorem. So essentially what we're saying here is find the potential function and evaluate the potential function at the endpoints. That's a nice way to evaluate a line integral. The third one, and this one is probably the most useful, the most practical, is pick any easier path. Yeah, turn it into a different problem. If f is conservative, you pick any easier path. And then it becomes less difficult or tedious.
So for example, if you have a super gigantic piecewise function with about a billion pieces, you could just use the shortest path from the first
Yeah,
point
make
to
a line
last
from the
point,
beginning point to the end point
and then
and evaluate the line integral along that line. All right, so we're not doing anything different here. We're still evaluating line integrals. We know how to do all of these. So I just want to look at a line integral and some various paths and talk about how we would evaluate these. So let me grab my pictures. So we're not actually going to evaluate this line integral. I just want to talk about the setup. And let me make this nice and big because I want to draw on these things. All right. So my suggestion from here on out, anytime you're doing a line integral, decide if your field is conservative. So, because if our field is conservative, we have more options for evaluating the line integral. So that's going to be my suggestion. When you're evaluating a line integral, test, see if the field's conservative, see if you can make your problem easier. So my first question here is f conservative?
Yes.
Well, here we're going to say f is 2x minus 3y plus 1 I hat minus 3x, whoops, minus 3x plus y minus 5 j hat. So this is m and that's n. Well, let's test. Partial of m with respect to y is negative 3. Partial of n with respect to x, negative 3. Conservative.
Yes.
All right. So for path A, do we even have to do anything now?
No.
No, it's
What is
zero.
this line integral?
0.
Line integral evaluates to 0. It's a closed path. So if this appeared on a quiz or a test, and you said f is conservative, the path is closed, the line integral 0, you'd be done with the problem.
Yeah.
You don't have to even do an integral. Which other one don't we have to do?
The other one's closed.
D is closed. Our field is conservative, so this evaluates at 0. Now this path, this is not a closed path. I would prefer not to have to, parameterizing a half circle, not that tough.
Just draw a straight line.
How could we evaluate this one?
Draw a line from -1 to 1.
Yeah, we can evaluate it along this line. And what's nice about this path? What is x? X equals 0. So dx equals 0. This whole thing goes away. This term goes away. Ah. So for B, pick easier path. So the integral will just be y minus 5 dy, and we'd go from y equals -1 to 1. That would be an easy integral. How about path C?
Same thing, just draw a straight line.
Draw a straight line. So we could do that one. I think I might, rather than parameterizing that line, not that it'd be difficult, I think I would do it, I would do this. That's supposed to be horizontal. Let me undo
We'll
that.
make a triangle.
So what is nice about this one?
You have two.
Y equals 2, dy equals 0.
So
That whole second integral goes away. On this path,
wait,
X,
y equals 1.
sorry, y equals 1. Yeah, that is 1. That's 2. Y equals 1,
Why does it go away? Why is it not just replaced by 2 value?
because dx would be 0. If x is constant, dx is 0.
What? Since when?
Very nice.
Yeah. Sorry, the second one would go away, right?
Yeah.
Y is constant. dy would be 0.
For the other one, it
For the other one, x equals 2, so dx equals 0. So the first integral would go away for the second one. And x equals 2. So we'd get two nice, easy integrals. Here, your parameterization wouldn't be difficult. I think this one might be easier to do as piecewise.
I guess it depends on what your resources available are.
Right.
Because you got a calculator, it'd be very easy to do one big piece.
You could also, if you wanted, you could pick this path.
That's the same thing though.
You can also do like a circle.
You can make it any.
Yeah, you could do that path. That wouldn't be bad. You could pick any. Yeah, you could do make a half circle between those two. Or it might not be too bad to evaluate that one just as is, because these are all linear terms, so it wouldn't be terrible. So what would our this path is y equals e to the x.
So the y's would be
So dy is e to the x dx. Yeah, that wouldn't be too bad.
maybe we just get rid of
Yeah, so that path wouldn't be bad by itself. All right, questions? All right, the last thing for today. We have been talking about conservative fields. It turns out we haven't talked about what they conserve. If F is a conservative force field. So if it's a force, if F represents a force and that force is conservative, for example, gravity, for example, electricity,
Gravitational force fields.
then F conserves energy. So a conservative field, if it's a force, implies the conservation of energy. So I'm not going to go through it. I'll post the notes on my website. There's also a video. It's called Calc 3 15.3 supplement. Conservation of energy.
What would happen if I didn't watch that? Would I die?
Yeah.
Eventually.
Okay.
Eventually.
Is there stuff on there that's on the test?
Well, it's all stuff that's on the test. It's all from chapter 15. So what happens in this video is we go from the assumption that F is a conservative field and show that implies the conservation of energy. So a conservative field implies conservation of energy, and I go through the demonstration to show that that's the case. It's nice because it uses topics from chapter 15, and it also uses some vector topics, Newton's second law, written in vector form, that kind of thing. So, and it's not long, but it's nice. You can see that if F is conservative, it implies a conservation of energy. And it's nice when we are coming up with some kind of description this, the stuff we're talking about in chapter 15 was invented to describe electricity and magnetism. And it's nice if the mathematical description of some physical thing also implies things that we know are true about that physical thing, like the conservation of energy. So it's nice that when the math and the physics actually are saying the same thing. The physics came up with empirically, math shows that that's true mathematically. All right.
Everything should be done.
But I mean,
You know it's bad. You have to start writing things like plural F. Like, that's just, we just